video is mostly about a process that I'm going to be using to extract the firmware from one of these tablets through its USB port. So at this point I've done a couple of videos about these graphics tablets and how they work inside, how you can hack them a little bit, how their magnetic protocols are a little bit like RFID tags. And I've been wanting to go a little bit deeper into that with these Wacom CTE 450 tablets that I happen to have a bunch of because they're cheap and easy to find. So this is the circuit board I'd really like to get firmware for. Why did I want the firmware? Well, I have a hunch. I wanted to see if it was possible to use one of these tablets to read an RFID card that operates at a similar frequency. And so that'll be a result for a completely different video. In previous episodes, when I was reverse engineering a Blu-ray drive, I just found the firmware available for download from the manufacturer. Later, when I was working on a portable audio recorder, I didn't really get the firmware out necessarily, but I started to get some clues in the form of a long response to a command that usually just returns information about the device. As far as I can tell, this device was never really intended to be upgraded by the customer. I couldn't find any downloadable firmware updates, I couldn't find any firmware updating functionality that seemed to be hidden inside of the driver packages. Oh, there's the CPU. It's got a little bit of crud on it. I didn't recognize this, and it doesn't seem to have any manufacturer markings that I would know about. But asked on the internet, and Lady Ada on Twitter actually mentioned that this is a processor series by Sanyo, later sold to onsemi. And the architecture is called the LC87. It's an 8-bit processor that you'll see in consumer, appliances and stuff like that. This 871 series is the one with USB. The public documents for the LC871 exist, but they're kind of sparse. And for example, it took a lot of digging even just to find the instruction set encoding, and I still haven't found any documentation on how the actual kind of debug/programming interface works. So that's what these test points over here are, TP3, 4, 5. I tried a lot of things, which are out of the scope of this video, and I couldn't get any kind of debug interface to show up on here, so I'm pretty sure that it's been disabled in this particular version. So that means there isn't really any official way to get the firmware out of this thing, so we have to get creative. As we've seen before, when you plug in any USB device, the operating system asks for little chunks of information called USB descriptors in order to figure out which driver should be responsible for the device. In order to read the firmware off through these descriptors, we're going to take advantage of the fact that those descriptors are inside the firmware. The descriptors live in the same flash memory that holds the code and any other data that's used by the code. So if we can somehow get this descriptor read to return more data than it's supposed to, then we can use it to read the entirety of the firmware.
Hi, my name's Colin O'Flynn, and I'm from Halifax, Nova Scotia, Canada. I designed this little board that I call the Chip Whisperer Lite. This board is designed for teaching yourself all about embedded hardware security research. So there's a whole series of attacks that happen when you take perfectly secure algorithms and implement them on physical devices. These attacks...
So the Chip Whisperer comes as a two-piece board that you can optionally separate and then reconnect using cables. This measure port is effectively an oscilloscope. There's a low-noise amplifier and a fast A to D converter. And then this other SMA connector, labeled Glitch, is connected to two MOSFETs, actually. This can kind of dump a bunch of your device's power, so the CPU is forced to operate without enough power for a few clock cycles until the capacitors can recover. As you can see in the middle, there's a big Xilinx FPGA. There's an ARM processor with an integrated high-speed USB interface. And so it comes as the kind of measurement unit here with the FPGA and everything else. And then it has a sample device under test that you can load code on to then subject to glitches and side channel analysis. So if you look at the Chip Whisperer tutorials, you can see how to use this built-in device under test in order to, for example, use power analysis to retrieve AES keys off of this device. So for example, you can load an encryption algorithm in this chip, and then by measuring very precisely how much power this uses, you can derive information about what the secret key is and eventually recover the key. And so this board is designed to already include the modifications you would want to make that kind of analysis easier. So this board has no local oscillator populated. Instead, it's set up so that the CPU derives its clock from the FPGA's clock generator. So the FPGA can keep its samples completely synchronized with the code execution on this processor. So the other critical modification this board has is they've actually changed the decoupling capacitor arrangement from the usual to something that's actually intended to amplify the switching noise of this chip. So on the Chip Whisperer's processor itself, you can see, typical use of decoupling capacitors, where you have power supply pins on the processor that are connected to a small local source of energy so that you really just try to keep the power as stable as possible. But if you look at the way the power is wired on this device under test board, it's totally the opposite. So for example, here's one of the device's power pins, and this trace is going not directly to a decoupling capacitor, but through a 49.9 ohm resistor. So here, actually, you can see the power coming in through these capacitors, then an inductor, then a 50 ohm resistor, then another bank of capacitors, and then this jumper, and then these capacitors. So the voltage at this side of R66, the 50 ohm resistor here, this voltage is going to be really as smooth as possible. They're really trying to clean that up. But then this side, this is going to be really glitchy because this is now connected to the processor with no power supply decoupling. So this arrangement here isn't intended to give the processor clean power. It's intended to amplify and isolate the switching and kind of power consumption noise produced by this processor, so we can measure these little differences in how much power the processor is using without necessarily just measuring noise that's coming in through this external power input. Okay, so getting this board ready for glitching. So there's the 12 megahertz crystal that we need to take out, and then we can see a few decoupling capacitors around the processor that we're going to have to check out and remove. I went ahead and made a high-res scan of these boards and traced out some of the important signals just by penciling them over in Photoshop, just so that I could get a better idea of where things went and how to work with this processor. So I have a couple of these Wacom tablets now that I've added my own kind of test points to for this setup. This one with the 1.16 firmware is the first one that I did, and then when I found another tablet with a different firmware version, I had to do it also. But since this is the second one that I did, and I was really just interested in extracting the firmware, I did a lot less rewiring on that one. So I did this earlier under my microscope that doesn't have a video camera, unfortunately, but it's kind of messy, but I did a little bit of PCB surgery in order to add some SMA connectors here. This one is for clock input, and these two are both connected to the power rails, the 3.3 volt supply on the processor. So on this side you can see that I've just desoldered the actual 12 megahertz crystal from this board. And the two crystal pins, one of them is being used as an input and one's being used as an output. So just using a series resistor and an oscope and a signal generator, I figured that out just by looking at the impedance of the pins, and the one that's not trying to fight back is the input. And so I added another little, in this case, 51 ohm resistor in order to just kind of series terminate the line a little bit and cut down on reflections, make the wave look a little bit neater. And then that's just connected to this SMA connector that I soldered right onto the ground plane of the board. So that gives me a clock input. I can just drive this externally with 12 megahertz, and this processor stays perfectly synchronized. Then on the other side, I've got two more of these little SMA connectors that I soldered to just bare spots on the ground plane. And then everything's just connected together with this big, ugly, thick wire just to try to reduce the resistance and inductance of everything. So these two are both positive 3.3 volts for the processor. And it's connected to the CPU at 3 points. So right here at C9, and then up here by this capacitor that's been removed. All three of those were decoupling caps that I removed, tied them back together here, and then under this resistor there's a cut trace, so this normally would have been supplying power to the CPU. Then this little stack of resistors here is acting as our current sense resistor. So the current being drawn across here turns into a small voltage signal here that's going to be measured by the Chip Whisperer. And then during glitching, we'll be using this same net here to just immediately discharge all the internal capacitance of this chip, meanwhile loading some power across this resistor. And then when we're done glitching, we release this, and then power kind of flows back into the chip's capacitance from this reservoir over here through this resistor again. In order to make this signal's AC content as clean a representation as possible of the processor's current waveform, we need the other side of the resistor to be very stable. So I ended up having to add a range of different decoupling caps here in order to filter out the high frequency and low frequency noise. And I added some more capacitors over here on the other side of the voltage regulator. So then the only other signals I needed to bring out on this big header up here, which is kind of overkill. I've got a couple of pads for ground, which double as mechanical anchoring to just hold this down. And then these two are reset and then a debug signal that I can use to synchronize with the firmware running on here. So the reset signal goes to this test point, and the debug signal goes to this test point, TP5. And those are both going to be used by the synchronization process in order to restart the processor and then kind of precisely start our own procedure once the processor reaches a particular point in its firmware. So if we take a look at the USB analyzer, we can watch this enumeration process and watch the tablet deliver these descriptors to the computer. So when the device is plugged in, right after this electrical negotiation where it figures out what speed to communicate at, you can see the operating system gathering several of the device's descriptors, starting with the device descriptor itself, and then moving on to configuration descriptors and string descriptors. This is the configuration descriptor request that we'll be glitching. This setup is an 8-byte packet that begins any control request and tells the device what kind of control request this is. So in this case, this is identifying the get configuration descriptor request. Then the in is an opportunity for the device to start sending back data. So this is where it starts answering the request. And then the out is used as an acknowledgement by the host after everything's finished. This transaction by transaction view of what's going on across the USB bus is usually the most useful way to look at it. But here we care so much about timing that it might actually be more useful to drop down to a logic analyzer and look at the individual packets. So USB is based on a shared twisted pair called D plus and D minus. And so this is used as a kind of half duplex serial line. One device talks at a time, and because of this, the host, in other words your laptop or a Raspberry Pi or whatever else is running the show, that device is responsible for determining everything about the timing of the bus. And immediately you notice this regular structure. As soon as the device has been plugged in and it comes out of reset, we see these packets happening every millisecond. These are the USB start of frame indicators. USB frames are these 1 millisecond units of time that are used in order to allocate bus bandwidth. And the USB host controller begins each frame with one of these packets indicating the frame number. All other bus traffic ends up being stuffed in between these frame markers. When multiple devices are addressed, especially with a USB hub, it's up to the operating system and the host controller to schedule packets within these frames. So here we can see the very first request that this issued was a get device descriptor, which is made of a few parts, the setup, the in, and then the out. And so here we can see the very first packet within that, the setup, that indicates that we're beginning a control transfer, immediately followed by a data 0 packet that actually has the contents of that setup buffer. These are the 8 bytes that tell the device what kind of a control transfer this is. In this case, we're reading a descriptor. So the USB host controller and the operating system have full responsibility for scheduling transfers on this bus. The device can't just tell us when it's done. The host has to periodically ask if the device has an answer yet. So the first of these queries, these in transfers, happen pretty soon after the setup. But the device responds with a NAC, which is to say, there's nothing here, try again later. So in this case, the host supplied the first in token pretty soon after the setup, but after the device said NAC, come back later, now the host is actually waiting a while, in this case about 2 milliseconds, to ask again. So by the time the next in token comes around, the device has an answer, and it replies with this data packet that actually contains the contents of the descriptor. And because this is a short packet, the host knows that there's nothing else left, and it can go ahead and acknowledge instead of sending more in tokens. So to have the best chance of success for glitching, we want to replicate this control request in a much more predictable and reproducible way. So that's where this add-on board comes in. It has a USB port that can be very precisely controlled and synchronized with the chip whisperer itself. I call it the Face Whisperer, since it's an add-on for the chip whisperer, but it's largely inspired by Travis Goodspeed's Face Dancer project. For convenience in the firmware toolkit, this uses the exact same CPU that's on the device under test board that comes with the Chip Whisperer Lite. But then right here you can see this is the USB host that it has control over. This is the MAX3421EE. It's a USB host controller that's programmable over an SPI bus. So this handles the electrical aspect of communicating over the USB twisted pair. It handles generating those start of frame packets, CRCs, all the low-level stuff that's really difficult to do in a microcontroller. But we still get so much control in the firmware over the exact timing of the transfers, and we can do a lot of things with this setup that a normal USB host controller would never be able to do because of the operating system. Besides the USB port itself, this board just has some odds and ends that are designed to help keep this AVR and the target processor synchronized. So this board is clocked by the 12 MHz clock generator on the Chip Whisperer. And then it also includes a buffer here that provides an isolated clock output on both of these SMAs that can drive the clock on the target board. It has a transistor here that can pull the reset line low on the target without really letting a lot of electrical noise back and forth. And then it also has an input that goes into a comparator here, so we basically have a trigger input so that this can very accurately wake up when an external signal crosses a voltage threshold. So here we've got the whole system hooked up. You can see the Chip Whisperer and the Face Whisperer add-on connected to each other. And then there's the modified tablet with its 3 SMA connectors, the clock on the top going to the Face Whisperer's clock buffer, and then the 2 voltage taps there going to the Chip Whisperer's measurement and glitching ports. And then those 2 other fly wires are just there for the reset and trigger signals. So there's a repository on GitHub for Face Whisperer that has the hardware designs for this board as well as the scripts we'll be using here. The firmware for this experiment on the Face Whisperer has 2 responsibilities: synchronization and issuing the get descriptor command. To synchronize with the device under test, we'll be resetting it and then reliably synchronizing to a signal that it gives off during initialization. And then only after that point, we set up our own clocks, including the USB host controller's frame timer. Everything is fully reset before each test: this microcontroller, the USB host controller, and the device under test. Once this firmware has stabilized the environment, it issues triggers that the Chip Whisperer can use to synchronize its measurement and glitching. And then it does this streaming control read, where instead of following the usual handshake sequence, we just continuously issue in tokens until something breaks in order to extract as much data as possible from the device. Since a lot of data might come back, instead of trying to store it in memory, we send it immediately over the serial port where we can look at it on the host machine. The other useful starting point you'll find in the Face Whisperer Git repo is this script that sets up the Chip Whisperer for this particular experiment. So we're starting out just by setting up the basic parameters for the Chip Whisperer Lite device and then connecting to the API. And then we're loading the firmware for this experiment into the device on the Face Whisperer board. So then that's going to set up the USB controller, and it'll be waiting for a command over the serial port before it actually starts the experiment by resetting the device under test. So a few of the highlights from the parameters set in this script. So right here we're setting up the clock generator to run at 12 MHz. This is what's providing the clock source for all the other devices in the system: the device under test, the USB host, and the Xmega running our firmware. And then the Chip Whisperer and the Face Whisperer microcontroller are using these 4 lines to communicate with each other. We have a serial port that we use for initiating the tests and for retrieving the results, which might include the firmware we're looking for. And then there's this trigger line that we use to synchronize the FPGA's glitching and measurement with the kind of environment that the firmware is taking care to set up reliably. So this section then controls the parameters of our serial connection between the Chip Whisperer and the Face Whisperer device. We're just using a blank line to start each test, since we don't have any information to communicate to the Face Whisperer in this case. Then the Face Whisperer does its thing and synchronizes with the device and sends the get descriptor. And then any results that come back end up going through the serial port again. And then this kind of magic token here is telling the Chip Whisperer to read up to 8 kilobytes over the serial port and to send that to the Glitch Explorer, which is kind of a GUI tool that'll help us find the right parameters for the glitches we're looking for. These are some default parameters for the glitching that I found work pretty well for this device, but every device will need some changes to the particulars of how the glitches are generated and when exactly you want to be glitching the firmware. And Chip Whisperer also lets you write these little Python one-liners to evaluate the responses from the glitching. So in this case, I've told the glitch descriptor that a normal response, so if the glitch doesn't really do anything interesting, I'll get something that has this successful result code and a length of 34 bytes, which is this device's config descriptor. But I want to consider a response to be successful, which will kind of make them easier to find in the results, if it's got a length that's longer than 34 bytes. So in this case, this Python mess here is looking for the number of bytes here in the total, and I'm just checking to see whether it's larger than 34. So if it's longer than a normal response, I want to highlight it. Okay, so if we run this script, it will set up the hardware and turn on our clock so we can actually start running some firmware. Alright, so we've verified that the firmware on our device is fine, and it's actually started doing some traces, which we don't really need yet, but it's fine. So this waveform that we're seeing is actually a measurement of the power consumption, or rather a measurement of the voltage. So when this goes lower, the power consumption on the device is instantaneously a little higher, and vice versa. So now we've got our external clock coming in at 12 megahertz. By default, this script enables both the measurement and the glitching, which are pretty much independent subsystems on the Chip Whisperer, and really we only need the glitching in order to get the firmware off, but the measurement lets us see what we're doing. It's our eyes in this operation. So before we start glitching, let's turn the glitching off and just look at what the power rails are doing when we answer this get descriptor request. So the whole idea behind the measurement side of the Chip Whisperer is to give you visibility into what the processor is doing. And so here I have the scope probe just probing the same power line that we're going to be measuring with the Chip Whisperer. And you can see some stuff changing, but there's a lot of noise and there's no synchronization here, so it's not really especially useful. So over here on the Chip Whisperer, we can see this power waveform that from very far away also kind of looks like a big block of noise. But we can actually zoom in and see these repeating patterns that really do correlate with particular parts of the firmware execution. Maybe this is like a main event loop in the firmware. And then if we look a little later on, these large power spikes are actually coming from the USB transmitter. So these are actually the power dipping quite a bit as it's spending the energy to switch the state of the D+ and D- lines on the USB cable. And so if I run this repeatedly, you can get an idea of how stable we've managed to get the environment. So the loop that's going on in the background has, I guess, a couple of different positions that it could end up in. So there's still something else going on that we haven't kind of fully locked down. But the offset of this reply is nice and stable. And if we take many traces, let's actually get them to stack so we can see them all on top in different colors. So now we can see not just one execution, but a whole range of possible ways that the firmware could execute, given very similar initial conditions, but with some uncontrolled variables. And so now we can get a better idea of what we have locked down and what might not be locked down yet, and try to improve the situation if we need to improve it. So to get somewhat broader view over this experiment, these are the waveforms of all the signals going between the face whisperer and the device under test, the USB reset and trigger here, and then the signals going between the face whisperer and the Chip Whisperer board. So the experiment starts with this carriage return over the serial port, and then the firmware on the face whisperer board starts doing its thing. So it resets the device under test by pulling its reset line low with that transistor. And then the tablet actually spends quite a while just getting its own stuff together and stabilizing its oscillator and clearing memory and whatever else it's doing. And so this takes 0.16 seconds. And then we synchronize again when we see this trigger signal over here. So when we get this trigger pulse, looks like on the negative edge here, we're sending back a little notification, just a new line back to the host to say, yep, I got the trigger. And then we start doing a USB initialization. So we start putting the bus into a reset state, And so this is a USB reset. It's kind of the standard way of telling the device to enter its default state. And then these next few commands here are actually just the kind of small USB stack that we're using. It asks the device for some information. We don't really need this, but it doesn't hurt, and it was more trouble than it's worth to disable this initial kind of enumeration. So we're doing some of the usual things, asking the device what it is and giving it a real address. So when this trigger signal goes high, that indicates that our actual experiment is beginning. And so this is actually our get descriptor with the super long length that we're going to try to get a really long response for. So we're asking kind of optimistically for a configuration descriptor, and hey, give us up to 64 kilobytes if you've got it. And so normally this wouldn't work, and the device would clamp this to the length of the descriptor that's actually available. But with the glitching, we hope to introduce a bug into that part so that instead of actually performing that check correctly, it just copies the long length into wherever it's storing the length and proceeds to send us that many bytes. So after the setup goes out, then we're just sending a notification over the serial port. All right, we're about to send the in. And here's the in token. And the first time the device says knack, come back later, but we come back really soon. And this time the device actually has some data for us. So we send the in PID, and then the device comes back and says, here's my descriptor, and it's just the normal length. And then to make it easier to parse our results and see what we've got, then we actually see that descriptor sent back over the serial port so we can pick it up with the Chip Whisperer's Glitch Explorer. And at this point, we don't really care what the device does. We're just going to reset it soon. So by looking at these packets on the logic analyzer, now we've got a really good idea of where the glitch needs to go. So we know that when the device gets this setup, that's when it starts actually processing the request. So it needs to be sometime after this. We know that it's also probably going to be after this point, because here when we ask, it's not actually ready to start giving us a packet, so it probably hasn't gotten around to actually processing. It might be partially processed at this point. And then soon after that, we're doing another in, and well, now it has it. So now we know that this is after it's done, and glitching it at this point probably wouldn't do anything noticeable at all. So this rising edge here is the time reference we'll be using on the Chip Whisperer. So this is 0 effectively. And our setup comes at about 180 microseconds. And then our knack is over here at 620 microseconds. And then the successful in is over here at about 730 microseconds. So this is really the interesting range. We probably want to home in on kind of the vicinity of this first knack, and that's where we'll probably see the firmware processing to get things ready for this in response. So the Chip Whisperer at this clock rate can capture about 500 microseconds with its buffer space. Set this offset to 0. So there's our acknowledgement. So this checks out. You can see that each of these little power spikes here, as it transmits the acknowledgement packet, corresponds to one of these edges where the output lines change state. So if we run this repeatedly, we can definitely see some patterns that look stable. All right, so let's run multiple traces again so we can see how this changes over multiple runs. So as you can see, things don't perfectly stay synchronized. There's a little bit of jitter here, and I've been trying to eliminate as much of that as possible to make it easier to see what's going on, but that isn't totally necessary. You know, it's still possible to deliver a glitch in a close enough spot, despite these things moving around by a few clock cycles. It definitely makes things easier to analyze when there's a little bit more stability. Okay, so now let's try turning on glitching again and see how we can disrupt the operation of this chip. So I'm going to have it automatically trigger a glitch once after every experiment is armed, and I can tell it the offset of this glitch relative to the trigger. So let's say we want to try glitching in the middle of this loop just to kind of test our hypothesis there. So maybe we want to glitch at 16 K points. So let's try putting in an offset of 4,000 here. Let's do that once. Great, so there's our glitch. So the glitch itself pulls the power rails low briefly, but then there's kind of this overshoot and recovery, and then you can see the processor isn't really operating normally for a while afterwards. So glitching it right there does no good. We just end up with no response at all. The processor doesn't come back. So at this point you can start just putting in different trigger offsets and inserting glitches and watching them happen. But this is really intensive trial and error, and thankfully there's a tool to automate this and search through this space of possible glitch locations and possible glitch parameters. So the Glitch Explorer window catalogs all the results from this experiment, and we can see a lot of results that weren't useful. It just didn't reply at all, and a handful of results where it didn't seem like anything really changed. And so here are a couple where instead of sending us the descriptor, it looks like it sent us some garbage, but it was a little bit longer than usual. So this might indicate that we've glitched the address where it's reading the descriptor from, or possibly something along those lines. It looks like there's something between about 7,000 and 8,000. So let's go to just that range and step every clock cycle and see where things start to get interesting. So at this point there's a lot of trial and error and using the Chip Whisperer Glitch Explorer in order to hone in on just the right parameters to make the most effective glitches. This includes changing the shape of the actual glitch pulses to be the most effective at disrupting the CPU without completely crashing it. And most importantly, you'll be adjusting the offset between the trigger point and the beginning of the glitch. Once we start glitching in generally the right place, we can start seeing the results quite fast. So here's a bunch of normal descriptor reads, and then, oh, here's one that started off normal but ended up being 128 bytes instead of 34. And then, oh, here's another long one. This one's 538 bytes, a few normal ones. And then that keeps going for a while. Here we go, this one's really long. Really, really long. And that looks like we've ran into some erased memory, and now it's kind of looping back into some active memory again. So there we go, 40,734 bytes. So that's actually all we needed. We can be done at this point. This is our firmware image. If we keep going, we can start seeing this happening pretty often. This processor has a 32K ROM, so any of these reads that are over 32K would give us the entire memory space, assuming it wraps around. But yeah, here we go. This is kind of our holy grail. We have a read that's a full 64 kilobytes. Here's what that glitching session looks like from the logic analyzer's point of view. So here's a bunch of fairly normal requests that don't give us long results, but here we can see a couple of the long ones, various lengths. You can see on the long responses that it actually takes us a while. We just keep issuing in requests and the device keeps giving us more data. And all the while, the firmware is actually running normally. This waveform on TP5 actually indicates that it's scanning the tablet for a pen. But there's still a state machine running that is happy to hand us back another 64 bytes of the firmware. Alright, so I just used a little bit of Python to convert this long descriptor read back into a binary file. We can see that this starts off looking like a USB configuration descriptor, and then down here we've got some other USB descriptors, the USB strings for a couple of different models. So this is the firmware's data segment. The compiler is just going to stick this data, the config descriptor, next to a bunch of other things that just happen to be needed by the firmware. And then if we go down, we should start to see something that looks a little bit more like code. So the last step here in generating kind of a properly formatted firmware image is figuring out where the beginning and end of flash memory or ROM or whatever this is, figuring out what address the descriptor was so that we can then sort of shift this image back into alignment. And that's going to depend a lot on the processor you're using. Here, this blank region is almost the end of memory, but we've actually got some other stuff here. There's a bootloader and kind of a little suffix page that's, I think, 256 bytes that the toolchain leaves there. So then what we're seeing right here is actually the boundary between the end of memory and the beginning of memory. So that's pretty much all there is to it in this process of extracting a firmware image through these glitched descriptors. So this technique is going to be most effective for really simple small processors that have, 32K address spaces or, 64K address space. But, you might even be able to use this on a larger system to dump enough of the firmware to get a foothold in the system. You know, if the USB descriptors are sort of close to the rest of the USB stack in the firmware memory, then maybe you can dump parts of the USB stack and find undocumented commands that let you read back more of the firmware, or, you know, find other ways of accessing the system. So that's it for this video. There's a lot more work that could be done on researching this hardware and trying to make it simpler. The measurement port is really useful for getting a sense of what's going on and kind of checking your work even if you aren't getting any useful results yet. But it isn't actually necessary, and I can imagine a much simpler device that just knows how to issue the special get descriptor requests and glitch the power. And I can imagine that device, if you could do it right, that could be very simple and effective against a certain class of USB devices. So once you have the firmware image, it's now possible to find, other undocumented features like commands, backdoors that you might not have been able to find otherwise. And these can give you more of an idea of how the device can work and how you can learn more about it. So in cases when you can't just download a copy of the firmware and the device isn't going to give you the firmware through the debug port, you might be able to use standard features in the USB stack combined with a little bit of glitching in order to get a copy of the firmware just through the descriptor read command. There's certainly a lot more we could do to get inside this firmware image and explore what makes it work. I've actually already done quite a lot of research on it, but that's a topic for the next video. Be sure to subscribe if you don't want to miss it. I'll see you next time, and as always, thanks for watching, and a special thanks to all my Patreon supporters who make videos like this possible.